All right, today we're starting the next section of these networks. So these are things called trees. So as it says here, a tree has no loops, multiple edges or cycles. If a tree has n vertices, it will have n minus 1 edges. And a spanning tree is a tree that connects all the vertices of a graph. So the term tree comes in because it's like the branches of a tree. And so the branches of a tree all spread out to different places, but they don't connect in between, and you don't have them looping around and that sort of thing. So that's why it's called a tree. All right, so it might be a tree might, look something like that, for example. That could be a tree. That's just one example. Now we can turn graphs into trees by removing some edges. So if, for example, I've got a graph like this, so A, B, and C, and they're connected, 5 and 2. We've got another vertex here that's called D. We've got another one here that's called E, and another one here that's called F. And so there's some connections between various things. Oops, that's not B, F. It's 4. So that's 4 there. There's a direct connection between those, which is 6. There's one here that's 3, and then there's one from there to there, which is 6. All right, so as you can see here, this is, when we have a look, we've got 1, 2, 3, 4, 5, 6 vertices. So vertices is 6. Edges 1, 2, 3, 4, 5, 6, 7 edges. So for this to be, so we want to convert to a tree. And so a tree has got to have 6, the number of vertices. So 6 minus 1 equals 5 edges. I can't spell. All right, so 5 edges to turn that into a tree. So we've got to remove 2 of those, and like it doesn't matter which 2 you move, provided you remove 2. So there's a whole bunch of different possibilities. So let's move. I'll remove different ones that are in the notes that's done differently. So I'm removing that one, and when I said it doesn't matter which ones you remove, this one here you can't remove. All right, because it's the only connection between B and C. So if you remove that one, then you can't get to C. All right, so I should have qualified that. Now, in terms of any of these others, it makes no difference. So let me remove, well, having said that, it does make a difference because I can't remove this one because then I've already removed that one. So if I remove this one, I can't get to E in any way. All right, so I'm then left with these particular ones here to remove. And so let's remove that one there, shall we? So when I've done that, what I've now got is I've got A to B, which is 5. There, that's there. Then I go here to D, which is 6. And then from D, I then go to E, which is 3. And F, I go from A to F, which is 1. All right, so that there is a tree. And as you see, if you look at the notes on the website, that's a different tree than the one I've got in the notes. Doesn't matter. The weight of this tree, so this is a spanning tree, because you get to all the vertices. And now we've got 1, 2, 3, 4, 5, which is one less. So the weight is just the addition of all of these numbers. So 5 plus 2 plus 6 plus 3, and then this one over here plus 1. And so this particular spanning tree, its weight's 5, 7, 13, 16, 17. So it's a bit smaller than the one that's in the notes on the website. All right, so there's a spanning tree, which then brings us to, and that fact that I said that one I've just done is one less than the one that's in on the website. We need to, sometimes the weight of the spanning tree makes a difference, so we need to know the minimum spanning tree. All right, and as it says here, this is a spanning tree with the smallest weight. How do we find it? Well, here's how we find it. We use this fella Prim, and we use Prim's algorithm. All right, so what is Prim's algorithm? So we start from a vertex, and again, it doesn't matter where we can start wherever we like. All right, and keep adding edges with the lowest weight until we reach our goal. So steps, choose your starting point, travel along the edge, which is the shortest distance to the new vertex, and repeat step 2 until all vertexes are visited. So here's an example here. And so given that A is the start of the alphabet, let's start here at A. So I'm going to start there. So when I'm at A, I look, there's 2, 5, and 6, and so the shortest is this 2 to B. All right, then from B, we've got 6 and 8 here. These are both pretty big numbers. All right, and so because these are big numbers, when we come back here and look there, there's a 5 and there's a 6 here. So if we're going to get to D, if I'm going to go to D from B, 6, that's further than if I went from A. So I'm going to go along here to D. So sometimes you're not actually moving on from where you stopped. Sometimes you need to, particularly at the start, right? Just particularly at the start, not exclusively at the start, but particularly at where you start. Sometimes you might have to, even though we went to B here, to get to D, we're better off going from A than we are from B. All right. So there we are. So now we're at D, and then from D, look, here's the short number here, 3. That'll take us up to C. And on the notes on the website, it's got written down these steps that we're doing. All right, so now we're up to C, and for C, well, we've already been to B, so we don't need to go back there. To E, we can get to E, and we'd go 5, and if we went to from D, that's longer, 6, so we're going down there, going that 5, and now we're here at E. The only vertex we haven't visited is F, and of course the shortest way to get there is to go from E2. So what we've ended up with then is this. We've ended up with B, A, D, C, E, and then down here to F, which is 2. So our weight of this one is 2 plus 5 plus 3 plus 5 plus 2, which is 5, 10, 12, 14, 17. All right, so the minimum weight or the minimum spanning tree on this particular network that we've got is 17. All right. Now, sometimes minimum spanning trees are important. And when we get to that, it's what we call connector problems. And connector problems, they're just minimum spanning tree problems. They're nothing more special than that. And just there's a cost of some sort involved. All right, so it might be the cost of connecting or a distance or whatever. So in this particular one, it says that there's 11 locations need to be connected to water, and a diagram of the distances in metres between is shown. Draw the minimum spanning tree. What is the length of pipe? So, if we're going to connect all these vertices together in with pipes, so that pipes cost money, so the least amount of pipe we need to buy to do it, better. All right, so we can start anywhere we feel like. I am decided that I'm going to start here. No reason whatsoever. It doesn't matter where you start, you end up with the same. So I'm starting here. The shortest way we can go from there is to here. That's 60s. And so then once we're here, we're now got this 40 that we can go. All right, you might think, well, what about getting up here, over here? Well, 70 is a lot more than 40, so we might be able to get there while we're going through some other places that work out shorter. Now, excuse me. Then from here, we've got these three, 50, 60, and 50. So I'll go down 50 to here. And then to here, I can go 70 up to there, but I could get to that point by going 60 to here. But I'm going to leave that for the moment because there's another 50 here, which was the same as that. So let me go here. And then, so now I'm there. At that point, it's only 40 up to there. So that's good, we can go up to there. And then from here, it's 50 back to there. So even though you might think, oh, 60 to there is shorter than going 50, 40, 50. The thing is, when we're going 50, 40, 50, we've gone through these two other vertexes on the way. So we've kind of got 3 vertexes in by the time we get there, for the price of just getting one. All right. So if I went there, that's 90. There is 110. So it's shorter to get to there. All right. Now, we don't need to go there. We've already been there. So that's all right. We do need to get to this one. It's 70 across there, but it's only 60 this way. So it's shorter for us to go that way than it is to go around. All right, we're now here, 40 down to there. From here, 60 down to there. And then 60 up to there. So there, in that, I've now drawn using Prim's algorithm the spanning tree. All right, so then what do we got to do? The minimum spanning, so there's A, part A, the spanning tree. That's what we're asked, I think, for A. Yep, draw the minimum spanning tree. There it is, done. It doesn't matter where you start, you'll still end up with the same one. All right, what's the length of pipe? All right, we just need to add those numbers up. So if I start at the bottom here, 60 plus 40 plus 50 plus this 50 here, go around this way, plus 40 plus 50, come there. Now I've got to go around this way to here, so that's plus 60 plus 40 plus 60 plus 60, and there we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got that correct. So that's a 60. All right, and then when you add that up, you get 510, and that's meters. All right, so that's trees, minimum spanning trees, and connector problems. All right, so if you have any problems, just email me. Have fun. And for those of you who've been wondering about the shirt, here's the shirt. I'm a maths teacher. Of course, I've got problems. All right. So have fun with that exercise. Email me when you need help with anything, and I'll record something for you.